Good morning, everyone, and welcome to today's webinar hosted by Bandweaver. My name is Marinus de Heide, and I'm delighted to be your host for this session. I've worked in international sales and fire safety technology for over 25 years, and it's a real pleasure to be part of a company that's continuously pushing boundaries in intelligent monitoring and infrastructure protection. Before we get started, quick bit of housekeeping. The session will be recorded and made available afterwards. Please feel free to drop your questions into the Q&A box throughout the presentation, as we'll have some dedicated time at the end to address as many of them as we can. Now, let's move on to the main reason you're here. I'm very pleased to introduce our speaker today, Mr. Richard Kluth, Managing Director of Bandweaver Technologies. Richard has over 2 decades of experience in deploying advanced sensing technologies around the world. His background spans energy, security, and critical infrastructure, with a strong focus on turning complex monitoring challenges into practical, intelligent solutions. Under his leadership, Bandweaver has become a global leader in distributed fiber optic sensing systems, with deployments in everything from tunnels and pipelines to smart grids and perimeter security. Today, Richard will be presenting 25 seconds to safety, rapid fire detection for critical infrastructure. Join us to discover how advanced detection systems with intelligent alarms and real-time thermal sensing can deliver earlier warnings, more accurate location data, and faster responses before small incidents become major emergencies. So without further ado, I'll hand things over to Richard. Richard, over to you.
Well, thank you. Thank you very much, Marinus, for the kind introduction. And good morning, good afternoon, good evening to you all, wherever you are. Thank you very much for joining our webinar. As Marinus gave details, the title is 25 Seconds to Safety, Rapid Fire Detection for Critical Infrastructure. I'm sure a lot of people are saying, why 25 seconds? As we'll see in the examples of some of our sort of case studies and analysing the technology, we often find that's around the time we're able to detect incidents with our technology, and it's a very early time. I want to put that in context as to why that's an important time, and why the importance of detecting as early as possible. So we'll firstly talk about, what does rapid detection mean? Why is 25 seconds important, and put that in the context of some fire incidents and what has been the timeline. We'll then give an introduction to the technology itself, our fiber optic linear heat detection, a little bit, how it works under the hood. We'll talk specifically about our smart alarms, our RapdiScan alarms, which are one of the key factors in how we're able to detect so quickly, both against conventional technology and also other competing fiber optic linear heat detection systems. We'll go into the details of some case studies, some real world examples, so we can show that. And then I'll finalize just with a few details about Bandweaver, about the company. And then finally, as Marina says, there'll be a Q&A session. You should see the Q&A button, as he said. Please feel free to drop questions in at any time, and we'll get to them at the end. So what is rapid detection, and why is it important? So when we say rapid detection, we mean detecting in the early stages of a fire. And that when I mean early stages, the stages when fire suppression can still be effective, we can remove fire risk and minimize damage. So when we're looking at the examples, that's always what we want to have in mind, is that we want to stop it as early as possible before it really develops. So there's not, although I talk about 25 seconds and we see that reoccurring, depending on the type of installation, different fire, different fire mechanism, there's not a specific time, and we'll look at different examples and show how fires develop, just to give some background to that. But as we said, we typically alarm around the 25-second marks, and in a number of cases, this has prevented critical damage. So we'll look at some of those. So what is not early? Have a look at some incidents where there has been substantial damage, and we'll look in a variety of different incidents: car parks, conveyor belts, road tunnels, and rail tunnels, and give examples of in what time frame that fire developed. Perhaps have a look at some of the shortcomings at the time, and then we'll move on to how our technology perhaps could have helped in these scenarios. When we look at each example, we'll look with this sort of time on one axis graph demonstrating. We've got time on this x-axis and then cost on the y-axis. So basically, the longer the fire is able to build and develop, the more the damage goes, and the less chance you have to use detections and suppression to bring that risk back down. So if we look example of a car park fire, typically in a car park, quite often we see the fire actually starts in one of the vehicles itself. So you have a period where that vehicle, where the fire is contained within one vehicle. And this is really where you want to have the detection. And this is really where your suppression window, effective suppression window is. Once you start to get flashover into other cars, you then enter this sort of yellow amber period where unless you catch it very early on, you're then past the stage where local suppression can be effective, and typically the fire department will get involved, but by this stage there's already significant risk to infrastructure. So in each of the examples we'll use this graph as a framework for looking at each of the incidents. So starting with King's Dock car park in 2017. This was in 31st of December 2017 in Liverpool in the UK. 1,150 cars were destroyed, a major structural damage. The building was demolished, and the total damage estimate was around 20 million pounds or 24 million euros. The initial cause of the fire was an electrical or mechanical defect within a vehicle, it's believed, and there was no automatic fire detection or suppression system. So in this case, the car arrived in the car park at 4:21 in the afternoon. There was smoke apparent on the CCTV 8 minutes later. So the fire started sometime within this. This wasn't noticed at the time, I have to say. This was in the incident report, but no one reported at this point. There was also flames visible at 37. So this is 16 minutes after the vehicle arrived. But the fire was first reported 22 minutes after the vehicle arrived, and this was a call to emergency services. So someone dialed, the number in the UK is 999. They called that, and emergency services were notified, and they were on site 8 minutes later, which is a fairly quick response time, sort of reasonable. But by the time they came on site, the situation was already out of control. It was, to their knowledge, the fire was only on level 3, but at this point, the flashover had become so extensive that there was a new vehicle catching fire every 30 seconds. So they were losing control at this point. An hour later of firefighting, CCTV then showed the fire was actually also quite extensive on level 4. No one was fighting at this point, but then they realized, that they were losing control, and then they endeavored for another 40 minutes, but withdrew from the building there, and the fire continued to burn for another 40 hours. So in this case here, it was about 20 minutes till emergency services and about half an hour before any firefighting. And this was considerably too late for that example. Looking at a conveyor belt example, this is 2006, Aracoma Alma mine, the 19th of January, which is based in the US. This was a horrendous fire with multiple fatalities and more than $290 million of damage. The cause of the fire was misaligned roller belts, and so build-up of friction, which started the fire. There was no detection close to the belts. As we'll see, the detection and suppression was ineffective. Detection was predominantly built around, I think, CO2 sensors, but was not trusted, and sporadic intervals. So as it wasn't trusted, action wasn't taken even when the sensor sounded. And we've seen this before in other previous webinars we've done in battery ones where they'd had false alarms before, and so actually, we've seen examples where suppression systems have been disconnected from detection. So it's really important that the owners have to have faith in the system. So in here, the belt was started at 4:20. And then at 5:05 was the first 5:05 was the first smoke observed. So there's a sort of 45-minute window there where the fire started. We're not exactly sure when it was, but that's the first observation. 9 minutes later, the first CO2 sensor. 15 minutes later that, heavy smoke migrating into primary escapeway. So this is potentially, more than an hour after it, and still action hasn't been taken. 5:39, the belt was stopped. 3 minutes later, the evacuation notice was given, and a formal emergency was declared at 6:21. But by this stage, 5:30, the situation was already really bad, and the heavy smoke, prevented people, both caused fatalities and prevented people from escaping. So you can see that's quite a long timeline before the right action was taken, nearly 2 hours in that case. Moving on to a road tunnel, the Mont Blanc tunnel fire in 1999, and this was a major event that really changed the way tunnel fire detection suppression was looked at in Europe. So this is 24th of March 1990. Again, a horrific incident with multiple fatalities and damages more than 500 million euros. The tunnel was closed for 3 years. The fire in this case was caused by a truck carrying margarine and flour. The fire burned for 53 hours with flames reaching more than 1,000 degrees C. So, terrible inferno. No suppression systems in this case, because of the sort of inferno-like nature of the fire. It prevented fire services from having the access they needed to effectively fight the fire. So in this case, the truck entered the tunnel at 10:46. Just 3 minutes later, smoke was observed. The alarm was raised relatively quickly in this case, 4 minutes later. But then, 4 minutes after that, heavy smoke had covered 500 meters of the tunnel, and by 11:10, the ventilation system unfortunately was blowing this smoke into the tunnel, feeding the fire and causing fatalities. And this is one of the big improvements we've seen is our systems can connect with ventilations to systems to prevent and manage the smoke in a way which can reduce the fire and not feed it and cause additional damage. So by half an hour, the smoke had reached the tunnel entrance. Long before this, the fire services really didn't have access to get into the tunnel, and then it burned for another 53 hours. So a really catastrophic event. Again, you would have needed to have suppression in these very early stages in order to have a realistic effect, a chance of reducing the scale of this incident. And our final historical incident is the Eurostar tunnel in 2008, 11th of September. As a result of this fire, the tunnel was closed for six months. Estimated cost between 50 to 100 million euros. The cause of fire here, a heavy goods vehicle was being transported on a train. It's believed it was over the height restriction, and the aerial of the vehicle came in contact with the overhead power line. This spike caused the train to stop, but there was no inspection, and so it continued. The train continued when the fire had started. There was some detection on the train, but no suppression system. So we'll see the timeline of how that happened. So the train departed in 3:36. The train stopped a minute later due to the power spike. So this is widely believed to be the start of the fire. The smoke was detected at 54, so about 17 minutes later. The train then stopped 2 minutes after that. Thank goodness in this case, it was early enough that people were able to safely be evacuated from the train, and they were able to bring the fire under control in this case. So the damage was not nearly as extensive as the Mont Blanc fire, but you still have a 17-minute window here where an effective suppression system could reduce this and massively reduce the risk and the damage experienced in this fire. So we say, well, how early do you need to be? How do this? So we'll see. We'll look at later on. We'll look at some case studies where we have effectively reduced that, and what customers see, what they want to see, and those sorts of timeframes. But before we go into that, give a bit of an introduction to what the technology is. So we talked about fiber optic linear heat detection. The underlying technology is called distributed fiber optic sensing, DFOS. It has a number of advantages. First, you get a lot more information. You get the precise temperature at all points along the fiber, so you're able to do a lot more with this. Including being able to manage the ventilation system. You're able to use this data to do advanced tuning of all of the alarms and zones, which means you can reduce the number of ellucients or false alerts. You've got very good accuracy to within 1 meter. With this tuning, and the smart alarms, you can have very early detection, which allows you to get a lot more information, have much better decision making. And we'll see how you can integrate with other systems so that the decision making and the automation can be much more effective. There's a number of physical benefits. Fiber optic sensors, they're passive, they have no moving parts. It's based on a glass fiber optic, which is immune to electromagnetic interference or radio frequency. So where there's high power sources, it's not at all affected by that. It's made of glass. They're not susceptible to corrosion. There's no power or electronics in the field, so it's very simple to install and very low maintenance, just a simple cable install. It's not impacted by movement, weather, environmental conditions, same way that the beams or aspiration sensors are, so it's very robust from that point of view. You can set it up in a loop configuration, so even if the fiber is damaged or cut, it can continue to operate with no reduction in capabilities. So it's a lot more robust than other technologies. And finally, the cost financial benefits. Because you just have a single cable installed, you don't have to worry about power electronics. There's a lot of reduced infrastructure, minimal maintenance. So throughout the lifetime, you have low maintenance costs, and the lifetime of the cable can be more than 30 years. Some of the telecoms cables that have been installed in the 1970s are still there. That's getting on for 60 years. You can have it up and running very quickly. It's a simple single cable install. And so there's a low total cost of ownership when compared to other technologies. So a number of different benefits. So how does distributed fiber optic sensing work? Well, the linear heat detection it uses a technology called distributed temperature sensing, which means it measures temperature at all points. And the fiber is the sensor. There's no points or specific sensors required. The controller, the panel that you plug the cable into, it makes the fiber optic sensitive to temperature, which I'll explain more on the next slide. It uses standard telecom grade optical fiber, so it's very cost effective, very readily available. And the technology behind that is known as OTDR, optical time domain reflectometry. Sorry, that's a bit of a mouthful, but you can think of it as being a bit like radar, but with light. So this diagram here gives a bit of example. So you have the controller, you have the fiber optic, which goes into the installation, and the fiber optic sends the pulses very rapidly into the fiber optic, about up to sort of 20,000 pulses per second, and then it's very, very rapidly sampling the reflected light back, hundreds of thousands of times per second. And by measuring the time of how long it takes the light to get back, you can pinpoint where that information has come to from within sort of half a meter. Typically for fire detection, we set it up for 1 meter. There's no benefit of the additional information, and it's more effective from a data optimization storage point of view to use 1 meter. And then if you run that in the installation, you can get temperature at all points, and so you can detect the fire very accurately to where it starts. So just to sort of be clear, the fiber is the cable. There's no dedicated sensors. You have complete coverage along the entire length, and it's very simple to install and very much less planning, because you don't need to worry where each sensor is. You're measuring everywhere. The cable, this is our FireFiber AET fire detection cable. It's no maintenance, totally passive, no moving parts, not susceptible to corrosion, design life is more than 30 years, immune to electromagnetic interference, no in-field powers or communications required, and very lightweight and flexible, typically 3 to 5 millimeters, so very easy to install. This next video, just a couple of minutes, will just give an overview of the FireLaser controller. We've got other webinars we go more into the technical details, so I'll just let this run. I won't say anything, and we won't cover any more on the controller itself in this webinar. But if you want to find out more, please do ask, and we do have other resources on our website that you can find it. So the cable we talked about, here's an example of some ceiling cable fixtures, which is quite often where the cable is put. Sometimes it's put closer to the assets, but in a lot of cases, it's the ceiling. It's typically offset. And here's an example of some different designs, but you can see it's pretty straightforward. It's a cable holder. Here's an example of some cables in some tunnels. So this one here, it's at the side. You can see the holders here. This one, it's on the ceiling level, and you can see a team here doing a testing commissioning process, heating with a heat gun there to test at that point. The typical sort of setup of the system, it's normally connected to the fire control panel via relays, and then in some cases Modbus over TCP or Modbus RTU to a PLC SCADA, where it may be connected to building management system, ventilation control, etc. And we'll see in some of the examples where that's the case. So moving on to the smart alarms, our RapdiScan alarms. As I said, these are one of the key sort of ingredients as to how we detect so quickly. So they are proprietary alarms. They're used on the FireLaser fiber optic LHD system. They allow for rapid detection, very accurate location, and very low levels of false alarms. There's three types of alarms. We'll go into the detail. They're all defined in the software, so you start and stop them wherever you want. You can have up to 1,000 zones, which gives maximum flexibility. I'll show the software interface very briefly later, so you can have an idea how that's configured. And they're all configured with a 5-second measurement time, so it's very straightforward across all our systems. It has the same measurement time, which is the right balance between having very good accuracy and very fast response. And we have a proprietary algorithm for maximizing the speed of detection while minimizing the false alerts that I'll go into a bit more detail of. So the three types of smart alarms, we have the absolute temperature alarm. This is probably the most similar to conventional sort of heat detection, where you have a temperature. If it goes over that temperature, then the alarm sounds. With ours, it's fully programmable for each zone, whereas often conventional heat detectors, it's not programmable. So we have an advantage there, but it's similar to that. We have our adaptive rate of rise. Other systems do use rate of rise. Ours, as we'll look into, it looks at the baseline. It has an algorithm that looks at the change in the thermal situation and responds accordingly, which allows it to react very quickly, but again, not to create false alarms when the slow moving detections. And finally, we have a hotspot detection where it measures the deviation from the average temperature in the zone, which can be very useful in very slow developing fires, where it would fall under the radar of the adaptive rate of rise. So often I get asked by customers, what values should we set? And it's very much dependent on each installation. But we do see patterns where, I'd say 80 to 90% of customers use very similar alarms, which is for the absolute temperature, it's typically 30 degrees above maximum ambient temperature. So in Europe, where the typical Northern Europe maximum is 30 degrees, people would set the temperature, 60, high 50s or 60 degrees C. Middle East or Asia, it may go a bit higher than that. And often the regulations dictate that you need to set the threshold 30 degrees above ambient. The adaptive rate of rise is typically set at 10 degrees C. So if it rises 10 degrees C within the period, it will trigger. And similarly, hotspot, around about the 10 degrees C part. And those allow for rapid detection, but not false alarming due to environmental changes. So if we look at each of the alarms in a bit more detail, so the absolute temperature alarm, it is what it says. If it goes over a temperature, it alarms. This is very much sort of in line with a number of standards that, as you say, the EN standards say, this should be set 30, I think 29 degrees C above the ambient. This is good at developing developed fires, or we have very severe overheating. You can program it in our case for specific environments. So as I said, you might set it lower in cold countries, higher in hotter environments, or different zones within the installation where they may be different. And it's typically the last of the smart alarms to activate, so the least responsive, but sort of your safety net, so to speak. So if we look at this graph here, this has distance along the fiber here. So imagine distance along this station here, and temperature on the y-axis. So if you had a fire here, and you set your T maximum, your absolute temperature at this value, wherever the temperature, whenever it goes above that, it will alarm. So in this case here, the temperature is showing in this zone here. So all of this would, any zone set up in this section would alarm. So that's sort of fairly straightforward to understand. The second one, the adaptive rate of rise. So this is very responsive, and to sudden heat build up in very early stage events, before you reach any critical thresholds, even before a fire condition is established. In some of our examples, we'll see you can have heat and still no flame, so you wouldn't get a flame detector or smoke detector detecting this because there's only heat present. So how does it work? It detects rapid changes, abnormal, something not normal, changes from the baseline. So it's constantly monitoring the baseline and making measurements of changes from that. So it's more responsive than a conventional rate of rise, and optimized to minimize false alarms. So if we look at this graph here, we've got temperature on the y-axis, but this time it's time. So imagine we're looking at the temperature at this point here and how this develops over time. So as you have a sort of small fire developing, it starts to increase. You've got changes in the environment that it's the adaptive baseline's following, but when the temperature, the fire develops and crosses that, that's when the rate of rise will change. And this can, as you say, typically set at 10 degrees C. So 10 degrees C is a lot quicker than waiting for 30 degrees C above the ambient threshold. The final alarm, hotspot detection. So this is at the earliest stage, and where the events can be slow and quite localized, where neither the other two alarms may detect it. This is in a number of cases been the first to detect. Again, before a fire condition is established, immune to ambient environmental changes. So if we look again, the graph this time, we're going back and you look at over distance and temperature. So we're looking at the temperature along the entire length. And you see here, you have your fire developing. You can see the hot spot here. You've set your delta T here. So when this developing temperature peak fire hits that's when you would get the alarm. And then you can see in this case, it's very slow, so that may not trigger the rate of rise alarm. So the three together provide a very powerful combination. You program these in the alarms. This is an example of our software interface. As I said, you can do 1,000 zones, you can overlap them, you can change the output, which relay where it starts, where it finishes. Each zone can have a number of different alarms. So you've got ultimate sort of flexibility how you want to do that. So a lot of people set zones to be quite similar, but in some cases, some zones are quite abnormal. So it gives you the flexibility to do both. So the sort of takeaway of the RapdiScan alarms, conventional alarms, they're fixed rules, slower to respond, and if you try and make them faster, they can be susceptible to nuisance alarms. With our RapdiScan, we have the proprietary algorithms with the adaptive baseline. You can respond very quickly, and these are proven in real-world fire tests and in actual fire prevention, which we'll look at now. Just a quick note reminder for anyone who didn't join at the start, please, if you have any questions, there's a Q&A button. Please do submit them, and we'll get to those at the end of the webinar. So we'll look at some case studies looking at the effectiveness of these RapdiScan alarms, and we'll look at actual fire prevention and also some field commissioning tests, which can be very instructive in showing how sensitive the equipment can be and how rapid. So we'll look at a number of different case studies. So the Turin Metro, a power station, Turkey, some road tunnels, and then car park commissioning in the Netherlands. So starting with the Turin Metro, this is one of the inspirations for getting the title of the webinar, as this was a project in which 25 seconds was key for alarming. So this was awarded to RAET, one of our partners in Italy, for the Turin Metro last year in 2025. They were replacing some older legacy fiber optic linear heat detection systems. They wanted faster, more accurate, up-to-date systems. They carried out an assessment. They looked at 3 different providers, and they did tests within the network to see how responsive the different systems were. And one of the critical factors was speed of detection. They wanted this detection in 25 seconds. So I'll just show we carried an interview with Sergio Sartini, who's one of the system experts at RAET, and he was involved in designing the system and installing. Marinus interviewed Sergio, and so we've just got a couple of minutes of Sergio talking on the project. Then I'll go into a few details afterwards.
Our customer has asked to find a solution to prevent fire and check the most important things is check the rate of rise when the train arrive and stay in the station, because we driverless, nobody can check what's happening on the train about the fire. But they had an old system in this station, in all station, and we are increase the safety with a new system from Bandweaver. Another technology, no, because the request is to check the temperature very close to the rail where the train has the brake, because when the train arrived to the station, the brake had a heavy work. So it's important to check the temperature under the train, very close to the wheel and very close to the brake. In this place, the metro has also the power supply. So they need something free for electromagnetic field and noise. So the optic fiber with laser is a good solution. And also they can they need to check also the temperature that while the train is moving along all the rail in the train station. And also, due to the position close to the wheel on the rail, the Bandweaver fiber optic is good because it's flexible, thin, but this kind of fiber has an external armature in stainless steel. So this is also heavy fiber. So the train arrives in the station, stop there for 25 seconds, close the doors and start again. So it's important to check the fire or the rising of the temperature in 25 seconds. Yeah, we have to check now, we have to check when the train is braking and when the train is in stop. So this is good because we can have a cycle time with Bandweaver unit also for 5 seconds, but in this case it's set to 7 seconds. And our competitor give the rate of rise every minute. That means the train can arrive, stop 25 seconds, the train start again. After 1 minute, maybe they can have the alarm. So this is not important. This is not enough. We have to know now So
Yes.
with this kind of unit, with the Bandweaver DTS, we have 7-second cycle time. So in 25 seconds, when the train is stopped in the station, we check 4 times, let me say, 4 times the rate of rise, and also the maximum temperature if you need.
Yeah.
In every station, they have a lot of PLC and SCADA system to check everything, not only the temperature, but they check TVCC, they check the voltage, high voltage, all level, water, sprinkler for the fire extinguisher. They have a SCADA where they check everything. This new unit was integrated with digital output and Modbus TCP with the PLC that check and verify everything, and also can activate alarm or not. But from the PLC, the unit is integrated also in the SCADA system. So for the first system, I was there. And first of all, we check the beginning and the end point to check for sensitivity zone with a electric cover, with heating cover, to check.
Yes.
So after this, we set the unit and then we simulate, let me say, fire with the electric cover, heating cover, to increase the temperature until 60 degrees. So the start before, this is important, during the test, before came the rate of rise alarm, because the heating cover is warming up very quickly, before we get the rate of rise alarm, and then we get the alarm temperature maximum alarm. So when we check if everything working well, the unit and the communication from the DTS unit with the PLC and SCADA. And then we close the circuit.
Very kind of Sergio to participate, give us the background to the project and his perspective. Just quickly touching on some of the points that Sergio discussed there. So he said the fire risk was the brake of the train potentially causing a fire. The fibre optic was installed close to the tracks, and the zones were divided in the different directions on the rail track. So one for the train going this way, one going for the other way. Because the trains were driverless, relied on automated technology, they're not, they need to detect abnormalities. There isn't a driver to make a decision and say, I can see signs of a fire, and not proceed in there or raise the alarm. So the trains are in station 25 to 30 seconds. So the fire must be measured within the 25 seconds before the train leaves the station. Only Bandweaver was able to do it within 25 seconds. The other competing systems took more than a minute. RAT were awarded the contract. The temperature alarms systems they used for that project were absolute temperature set at 55 and adaptive rate of rise at 9 degrees. So see, the adaptive rate of rise was critical to this response, and instead is integrated into the SCADA system. If we look at another project by RET, we can look at one of the most advanced SCADA system integrations they've done. So this is the Santa Lucia tunnel, which is the widest tunnel in Europe, nearly 14 meters wide, has 2 cable sensors on the roof. We monitored 8 kilometers with 3 systems to give full controller and cut redundancy. You can see an example here of the team in the substation, the unit in the rack, the touchscreen LCD. So again, this was integrated with the SCADA system, and this is one of the most advanced I've seen, where they set up zones every 10 meters, so 982 zones connected to multiple systems, extinguishing the ventilation and lighting system. We weren't the only fire detection system on site. They also used smoke detection, beam-based, and CCTV flame detection. but we were the only ones connected to the fire extinguishing system because they had sprinkler heads every 10 meters, and they wanted that level of accuracy so they could really pinpoint the suppression. So in the event any zone goes, you can, have the full suppression system all focused at the point where the fire is, rather than, putting it across the whole tunnel and running out much quicker, lower pressures, etc. So it's a really, really great example of how this technology is used together with the suppression system. Looking at the road tunnel in Turkey, this is the longest 4-lane tunnel in the world, eight tunnels along the length of the highway, a redundant loop configuration. And the reason for looking at this tunnel is we've got some video footage of the commissioning test, where you can see the fire pan test that they do in the tunnel, and you can see how quickly the system detects. So it's a little bit shaky. It was recorded using a mobile phone in the control room, but what you'll see is they light the timer starts, they light the pan at 6 seconds, and it's detected within the SCADA system at 36 seconds. I won't talk over it. I'll let you see, and you can see an example of how quickly it detects at the commissioning test level. Hopefully that gives you an example of the sensitivity. Our final example on road tunnels is an example in India where the FireLaser was installed, and it actually successfully detected a fire within 10 seconds. It was connected to the suppression and the ventilation systems. So the fire was extinguished and all smoke cleared from the tunnel within 180 seconds. So no significant damage, very limited downtime, no reporting in the media, no reputational damage. So it shows, how effective the technology can be when integrated with the suppression system. And this could have been one of those $100 million fires that was extinguished at before it really could take hold at all. Moving on from road tunnels, looking at conveyor belts in a Yenikov power station. This is a coal fire power station. A lot of coal moves through critical power infrastructure, the highly flammable product. More than 20 kilometers of belts involved in this. They needed advanced visualization, which we won't go into in this presentation. It was based on a single 10-kilometer unit with 4 channels, so you could have up to 40 kilometers. They configured 740 zones, each 30 minutes length, so they used about 50% of the capacity. So they had 20 kilometers of monitoring. The RapdiScan, the absolute temperature they set between 57 to 61 degrees, and the adaptive rise quite low in what I've seen, 5 to 7 degrees C, and it was integrated with the Panasonic CCTV. We've got some photos here, photo in the control room, the unit in the rack, the fiber installed, a training session. When we look at the fiber install here, you can see this is the conveyor belt. These are the rollers, and this is the source where the bearings may heat up. So they've got the cable as close as possible to the area of the heating. And again, a successful fire prevention detection here. Hot roller was detected using the rate of rise alarm. The zone was isolated within 30 meters. The maintenance team went to the zone upon alarm, used the thermal camera to corroborate. It was glowing hot, so no further damage or fire. Roller replaced. Again, this could have been a massive incident, but was stopped before the fire was allowed to develop. So our final example is looking at car parks, and the reason for this is in the Netherlands they do car park commissioning tests that really demonstrate how sensitive this system can be. So if we look at this example, this is an indoor car park. They use heat detectors because it's challenging for smoke detectors. This fire nearly 7 kilometers. They have 8-meter spacing between the cables. So when they do the commissioning test, they need to test the commissioning at 8 meters. So you can see some examples of the cable at the ceiling level, typically sort of 2.5 to 3 meters. You can see the cable is very flexible, as we said, it can do tight bends. And so in the Netherlands, you can choose your spacing, but you have to then detect a fire pan to show that you've got effective detection. The pan's relatively small, it's 500 by 500. Depending on the wind speed, it either has 1.2 or 2.4 litres, ceiling height 2.5 to 3.5. The rate of rise in hotspots typically 7 to 13, 10 to 15 is normally the levels. In this case here, this test here, you can see the cable is at the ceiling level here. The other cable's 4 meters the other side, so they're 8 meters apart. So this is 4 meters from the pan to the cable there. So if we look at our partners SenseTech lighting the fire, in this case the wind speed was above 1.6 meters, so it was a 2.4 liter, and the detection was around about 25 seconds in this scenario. You can see they're varying from 1.3 up to 1.8, and you can see the detection there happens within 25 seconds. We have some data here where you can see, because the system gets data, we've taken a trace. You've got the distance along the fiber here, and you can see the heat developing. This is the time at the top. So you can see here, it starts 5 seconds, the fire's lit. You can see the fire starting to develop. Here, in this case, it was set to 7, the rate of rise. So it detected at 34 seconds for this particular example. In this case, you can see the wind actually starts reducing the fire. It's blowing it around. So you can see how small the fire is, that even a relatively small amount of wind can affect it. The fire builds back up, and so it peaks round about, I think, sort of two minutes at 25 degrees C, we'll see here. So the absolute alarm would still never detect for this fire pan test. So the only chance you've got of detecting is with a rate of rise. And you can see it's still sort of burning. I think it peaks at somewhere at 12, 15, nearly 16 minutes. Yeah, there you go. It peaks there 5 minutes later. So we detect well into that, even that small fire pan test. So these tests are mandatory. Traditional copper LHD systems are not sensitive for pass. So because of these regulations, because they want these super sensitive systems, it means that fiber optic linear heat detection is becoming a standard within the Netherlands in car parks. So just to sort of summarize the case studies, you can see all of them are 25 to 35 seconds. We were consistently rated as the fastest system, and the RapidScan alarms play a key role in that. Early detection is critical. A few seconds can make all the difference. But detecting's not enough. You've got to do something about it. So increasingly, we're saying this needs to be with automated suppression, so that you're taking action within that time frame. So the whole system has to be automated. And you have to have complete confidence in the system to have an automated system. And we find, we across the board, we do have a very high confidence level. Our customers do. So I'll quickly finish up with a few Bandweaver facts. We've been around more than 20 years. Thousands of systems and kilometers of fiber are installed around the world, all based on DFOS, distributed fiber optic sensing, distributed temperature sensing for the linear heat detection systems. We have offices around the world. I'm based in our UK office. We've worked with companies all over the world, big, small, many different sectors. So we're very versatile technology. We approve to global standards across the different industries. So example of some of the standards we work to there. And in conclusion, we've seen other ones. Fire risks, we've got into details of some of these things. Fire risks have been changing over the years and growing. And fiber optic linear heat detection is really good technology for dealing with that. So it's robust and reliable. We're seeing it more and more. It's one of the quickest methods of detection. And we've been doing this for a long time. But even though we've been doing it for a long time, a lot of people are still hearing about the technology for the first time. So hence the reason for doing these webinars and trying to explain how effective it can be. So we've got a number of resources. You can go to our website. You can see this webinar and previous webinars on our website. We have other videos explaining the technology, and there's various other downloads. So thank you very much. I've got Marina's and my contact details now, and we can open it up for questions.
Thank you very much for that, Richard. That's a lot of information to absorb. So therefore, you can visit our website to see this again in your own time. And we've only got time for a few questions, as we've nearly taken up a full hour. So one of the questions we had was, what's the maximum length of cable we can monitor? So as you've probably seen in the presentation, we can do a maximum of 4 channels at the moment, and 10 kilometer per channel, which makes a total of 40 kilometers on one unit, which is a lot of distance to cover. So I don't think there's anything to add to that, is there, Richard?
No, like you say, 40,000 measurement points. That's a lot from one controller.
That's a lot, yes. So what happens if the cable gets damaged? Damage to the cable can, of course, occur. When that happens, there will be an alarm set at the unit, so you know exactly the point of damage. And you can repair the unit with something called a fiber splice unit, which is quite common in the telecommunications industry. So it's a pretty standard procedure. And
Good to emphasize, that the cable is very strong. We don't often get many cable breaks, but in some scenarios, for example, in car parks, oversized vehicles where they're going across the ceiling and something's dragging across there, there's not much you can do about that. But it's but as you say, Marin, it's easily repaired even if that does happen.
how easy is it to install? I think Richard covered that already in the presentation itself. But one point I wanted to make clear as well is we always say it's lightweight, but what is lightweight? Well, our cable actually is only 21 kilograms per kilometer, which is a fraction of the weight of other similar linear heat detection cables, and therefore it's easy to manage by people on site.
Nothing to add there.
Absolutely. How to integrate into other systems? There's 2 ways to do that, really. One is via relays. There's 50 relays already available on the unit itself. And the other way to do this is Modbus over TCP. The relays are normally used in combination with fire panels. The Modbus is more used with SCADA type of BMS systems.
I mean, if I was going to say, looking across our sort of installations, generally, what we tend to find is for smaller installations, there tends to be relays, the fire control panel. So warehouses, factories, typically that. But where you have a large sort of critical infrastructure project, tunnels typically always have the SCADA system. Anywhere there's a building management system, you want to also have influence on perhaps the lighting or the ventilation system. It's used in conjunction with that, and you get a lot more information over the SCADA system than you do with the relays. So it does allow you to fully, benefit from the fact that you've actually got the temperature information and what you can do with that. So yeah, absolutely.
I realize we're going over time as well, so I think we're going to go to the last question. Can this be installed only in new builds or in existing systems? So, of course, the answer is you can also install this as a retrofit in existing systems. We're doing a lot of conveyor belts at the moment where conveyor belts are already in place, and we're retrofitting the cable to it, which yeah, gives them a great advantage in the fire detection system.
I think because as we've mentioned a few times, the cable is pretty simple to install. It makes retrofit, a very accessible and economical opportunity to do that. You don't have to put any power in there. You don't have to put any comms network. You don't have to run other cable backs. It's just a single one. So yeah, it's we see that. It's probably our most common form of installation, I'd say, Marinus, is retrofitting, not necessarily when the project is first built.
I think that was it for today. As I can see, a few people are already leaving. They probably got other meetings to attend. Uh, Thank you very much for watching. As I already mentioned, and Richard as well, this will be available on our website. If you got any questions, please email them to us as well. We'll be happy to respond to that. Anything for you to say, Richard, to say goodbye?
No. Thank you very much. Apologies. I think I went a bit longer than I didn't give quite enough time for questions there. I think as you said, perhaps a bit too much information for the session. But yeah, we'll please do. Yeah, we'll get your questions via email. Get back on that. And as Marina says, that the webinar will be on our website to watch again if you missed anything or want to see anything again. Otherwise, we're very happy to we'll follow up and take more questions afterwards if you think of something afterwards.
Okay. Thank you very much.
Okay. Thank you, everyone. Have a great day.